So if you remember, in the last class, we started this discussion of error discussion and error correction in the data uh, streaming, data communication technology. And we've seen there are method of first detecting the error. So one simple method is you send the data and it's photocopy and check bit by bit, one by one. Okay. So the important task is to identify the error. Okay, actually error bit, and then to rectify it. So error detection uses the concept of I told you what is the concept of redundancy. So instead of sending the data two times on the channel, which will require the additional bandwidth, at the same time the system will become slower because bit by bit checking will happen. So instead of doing such a tedious job, such a lengthy job, such a long and tiring job, what one can do, one can add the additional checking bits, okay, either towards the right side or towards the left side of your data, and those bit will tell the receiver if the error has occurred in the data stream or error has not occurred onto the data stream. So if suppose there is no error in the data stream, then those bits will be discarded and the data will be then processed. If there is some error as indicated by the error bits, then the receiver will again send the message to the transmitter that the whatever I have received is corrupted information. Please resend the information back. Okay, so that way, in this way, the bandwidth can be saved, and the whole system can become more efficient. Right? Clear?
Yes, sir.
Hmm. So extra bits will be discarded as soon as the accuracy of the transmission is determined. So since they are discarded, they are redundant to the whole information, whole process, and that's why this technology is called as the redundancy bit checking method. Okay, so this technique is called a redundancy because the extra bits are redundant to the information. They are discarded. These extra bits are discarded as soon as the accuracy of the information has been confirmed. Okay, there are four methods of the error detection and correction method. Okay, so the simplest method which we will discuss in a while is the vertical redundancy check method. This is the simplest method. There are drawbacks, a few limitation of this. So and hence another method was devised, longitudinal redundancy check method. Again, there are limitations. So cyclic redundancy check method. Again, there are limitations. So checksum is the method which is widely accepted. Okay, so these are the four method. Your book B.A. Frozen book also describes these four methods in detail. So I will be I'm sticking to the Frozen book, and I am also discussing these methods in detail. So I will start with vertical redundancy check method. Okay. Now, what is this vertical redundancy check method? Is as follow. Okay, so it is also called as parity check method. Now, what this will do here, a parity bit. I told you in all this redundancy check method, extra bits are added either towards the right side or towards the left side of the whole information. Okay, so in this particular method, one bit is added. Okay, here, extra bit is added, appended to the every data unit so that the total number of ones, in the unit, this unit means data unit along with this checking bit. So, whole number of entire number of one should become even. Okay, let me give you an example. Suppose you want to transmit letter small a. When you type small a onto the electronic devices, whether it is a mobile phone or laptop or computer or any other device, SMS, WhatsApp, Telegram, wherever you write small a corresponds to decimal number 97 in the ASCII code, and this ASCII code decimal number 97 will be converted into the binary number, which is represented by this 11000001. Okay, so this is the binary representation of ASCII number 97. Okay. Now here, if you look at this binary number 97. How many one are there? One bit, right? Okay. Now what this method tells us that if you have odd number of one present in the data, if you have odd number of one present in the data, then you add one more one. You add one more one. You append one more one in order to make the whole data. Data means information along with this parity bit, along with this checking bit, so that the number of one should become even, right? So since there are three ones here, so what you will do towards the right end, here the number of ones is 3, odd number. So therefore this when this 97, when this number will go through this uh, parity check method, so the parity check device, parity check device, that block, that circuit, it will introduce one more one in order to make the one number of whole even number of ones into the data strip. So VRC system will count the number of ones in the data, and if the number of one is odd, then it will append parity bit, a one in this case, to the end, so that the total number of one is now 4, an even number. The system now transmits this entire expanded unit, means data unit plus this extra bit, which is one here, to the next part of the communication channel. Total number of one will be 4 here. Here is the example. Okay, so this is another example. Okay, so see, this is the data which is having odd number of one. So your parity bit checker, your redundancy checker will check the total number of ones. So if it is on odd, then it will add one more one. Now you see one more one is added here. So this whole block is the data, and this one is appended because total number of ones were odd previously. Now if you see, if you look at the whole data, the expanded data, total 4 ones are there, which is even number. Now this expanded data will flow through the medium, and then it will be received at the receiver, and receiver circuit, again there is a checker, okay, redundancy checker. That checker will count the total number of ones. So if total number of ones are even, then the receiver will assume that no error has occurred, and therefore that data will be processed, and the extra one will be discarded. So remaining data will be processed. If the one number of one says even here, then what will be introduced by parity checker? If the number of one is already even in the data unit, what will be introduced by the parity checker? This whole process is to make the number of one as even in the whole process. This is simple algorithm. Nothing great is there. It's a simple algorithm. Okay. Of course, once upon a time, this was a very good technique when there were so many mess were happening in the data communication system. So this was a very good technique, time saving technique, bandwidth saving technique. Okay. But there are failures, there are limitations of this as well. If already even number of ones will be there, then this parity checker will append 0 here, because the whole algorithm is based on to make number of one as even. If odd number of ones are there, then one more one bit having one will be introduced. If even number of ones are already there, then 0 will be introduced. Okay. So at the receiver, so what receiver will receive? See what was transmitted. This was transmitted 11000001. So this was transmitted. Since there were odd number of one, so what parity checker will do? Parity checker will introduce another one here. Now if you look at this total number of ones, so you see 1 2 3 4. So 4 number of ones are there, which is a even number, and hence now the data will be processed from the transmitter end, and it will be received at the receiver end. Receiver will check the total number of one. If it is even, it will process further. If it is odd, receiver will send back the message to the transmitter to kindly resend the information back. But there is a problem. What is the problem? Can anyone tell me what will be the problem with this technology? Tell me on what idea, on what basis this whole technology depends on what basis this whole technology depends on. Just to see, concentrate on my statement, just to see the number of ones, right? If number of ones are even, then receiver will be sure receiver will be sure that no alteration in data has occurred. Am I right? If 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 number of ones are even, then receiver will understand that no alteration in data has occurred. Am I right?
Yes.
If receiver sees odd number of one, then receiver will understand something has happened with the data. What is the problem? Here, if you see in this whole data, there are four number of ones. Suppose, for example, let me take the example. Suppose this second bit from the left end. Suppose, for example, this one bit number, this bit one gets altered, gets corrupted, and it becomes zero. Gets altered and becomes zero. And this third bit from the left end, this zero bits gets corrupted and it becomes one. This one becomes zero and this zero becomes one. Now you tell me how many ones are there. Still even number of ones will be there. Okay, so if there are two bits getting altered in the process, okay, then this method will not be able to detect the error in the data. So this method is valid only if single bit gets corrupted. If single bits error, so this is valid. uh, Very well method, but valid only for single bit. So what if instead of 1 0 0 1 1, which is having 4 1, the receiver sees this. Now here if you see 3 4 5, so this third bit got converted into 1. So here I am working with single bit error. Okay, in this example, so this zero bit number third got corrupted and it got converted into one. So total number of ones are odd. Now the receiver will understand something has occurred, some error has occurred. So the receiver will send message back to the transmitter to resend the data. Understood? Understood?
Yes, sir.
So very well method, very good method, very well designed method to check the single bit error. Okay. Then the receiver will count the total number of one, which is odd number. Receiver now understand that error has occurred into data somewhere. Okay, and rejects the whole data unit. Okay, rejects the whole data unit, sending back the message to the transmitter that kindly resend the data properly. Okay, some more examples. Suppose we you want to send this information 1 1 1 0 1 1 0, and this is another information, this is another. So can anyone tell me what should be appended in this data number one towards the right, 0 or 1? These are separate data. This is one data unit which will go first. This is another data unit which will go later on. This is another. There are three separate data. So I'm talking presently data per data. Okay. So for this data, what should be appended towards the right hand by the checker? 0 or 1? You count first the total number of 1. If it is odd, one more 1 will be added. If it is even, no 1 will be added, 0 will be added. So for first data, what should be added? What should be appended at the right end?
There are 5 ones, so one will be appended.
Right. And in this case, already there are even number of ones. So 0
There,
should be appended.
yes, sir.
Okay. What about this case?
Zero will be appended.
Right. Okay. So for the first case, you will append 1 because there were 5 number of ones, which is odd number. So you append 1. to make even number of one. In this case, already there are 6 ones, so 0 will be appended. In this case, 4 ones were there, so 0 will be appended. Understood this method? Understood?
Yes, sir.
Okay. So that was a simple technique. Okay. So VRC can detect all single bit error. This is what I told you just now. For single bit error, this is a very good, very efficient system. It can detect burst error if the total number of errors in each data unit is odd. One more example. If suppose odd number of bits are changing, if suppose odd number of bits are changing, then also it can detect. Okay, but if even number of bits are changing, then this method will be not uh, efficient to give you if error has occurred or not. Okay, understood? So it can detect the burst error if the total number of error in each data unit is odd. Okay, if odd number of bits will be changing, if odd number of bits are changing, then it can detect. If even number of bits are changing, then it will not detect, right? VRC, the vertical redundancy check method, will not be able to detect errors where the total number of bits change is even. Understood this slide? Hello?
Yes, sir.
Okay. So I suppose you all have understood properly this VRC method, right?
Yes, sir.
Now, very much similar to what we have seen, VRC method is the longitudinal redundancy check method. So very much similar with slight modification, advanced modification. So now that method was very good. But if you have a long stream of data, just now we have seen 8-bit data, 7-bit data. But if you have a long bit of data where parallel communication is happening, so many information, then again it becomes a tedious job for the checker to count the total number of ones. So if instead another method can be devised which will take care of the speed of the thing, then the system will become fast and more efficient. Okay, so in this method what is done, a block of bits is organized. Okay, so suppose if you have a long stream of data, 32 bits. Okay, now what you can do, if you have 32 bits, so you can divide this 32 bit into 8 bit, 8 bit, 8 bit and 8 bit. So four 8-bit information you can arrange, right? If you have a 32 bit of information, you can break those 32 bits into 8-bit, right? Understood?
Yes, sir.
Okay, you can divide 32 bit into 8 bits, and then you can apply the same VRC method, rows and column wise. Okay, and then calculate the parity bit for each column, and set of this parity bit is also is sent along with the original data. Okay, now how this is done, let me give you the example, then you will understand. Now suppose this is the whole data string which you want to send to the receiver. So how many bits are there? 3, 4, 5, 6, 7, 8. So this is 8-bit, another 8-bit, another 8-bit, another 8. So these are the 32 bits of information. What I told you, you break the 32 bits into 8-bit, arrange them in rows and columns. Okay. So how to arrange this? So let me just arrange this properly. So let me write first here. So first 8-bit I will put in row 1. Second 8-bit I will put in row number 2. Third 8-bit I will put in row number 3. Fourth 8-bit I will put in row number 4. Have you understood up to this point? Let me know. Understood or not? If you have not understood, I will repeat again. What is this
Yes,
method?
sir. Understood.
Huh. So what is this longitudinal redundancy check method? So in this method, a long stream of data is broken into small stream, and then every stream is arranged in a particular row. Okay, first row, second row, third row, fourth row, like this. And what is done then is, so I'm arranging this. So this 8-bit I'm putting in row 1, next 8 bit row 2, third 8 bit row 3, 4 row 4, like this. Okay. Then what? Can you see the mouse pointer which I'm moving around here? The row 1.
Yes, sir.
Okay. Now, what is this method uh, is based upon? Is that now you start from the right extreme end where I'm moving the mouse cursor. We start from the right extreme end and count the total number of one in that column 1. Now you tell me how many ones are there in this column? Column 1. How many ones are there?
4.
4, which is an even number, right?
Yes, sir.
So if total number of ones are even in a particular column, then you append 0 here. You append 0 here. Understood? You will write 0 here. Here, below this line. Understood? Hello?
Yes, sir.
Now come to the next column. How many ones are there in this column? In this column, how many ones are there? Only one, no?
1.
So what you will append here?
0.
No, no,
No, no,
one.
no. Odd number of 1. So 1 will be appended.
Right. Now come to the next column. How many ones are there in this column? Two ones are there, no?
Yes, sir. So 0 will be appended.
0 will be. Come to the next column. 0, 1, 1, 1. Odd number of ones are there. So what will be appended?
1.
1, right. 0, 1, 1, 0. So even number of ones, so
0
0 will
will
be.
be appended.
And here odd number of ones, so
1
1
will
will
be
be appended.
appended.
Even number of ones, so 0, and odd number of ones, so this will be appended. Please check if this is right. Understood? Right?
Yes.
Okay. So now, what this method is based upon? So you convert the long data stream into smaller data stream, arrange them in rows and column wise, and for every column you check the parity bit. Okay, you check the number of ones. So if number of ones are even, then you append 0. If number of ones are odd, then you append 1. Okay, and then you collect these extra bits here. Okay, and these extra bits, which is called as the LRC bits. Okay, longitudinal redundancy bits, check bits. These extra bits should be appended towards the right extreme end of the that long data string. Okay, so now your data will become, so data unit plus LRC will become like this. Okay, so first 8 bits were the original information, and last 8 bit is the check information. Okay, so this is what, so last 8 bits are the LRC bits, and first 8 bits are the data units. Understood?
Yes, sir.
Okay, and then this will be transmitted. Okay, suppose for example, so this is what is transmitted. Okay, and this is what is transmitted from the transmitter end, and this is what will be received by the receiver. Now suppose for example, here if you see, purposely I'm changing few bits here in blue italic way, so that you understand some bits got corrupted here. Now suppose this 1 1 becomes 0 0, this 1 becomes 0, and this 0 becomes 1, this 1 becomes 0, and this way. Now for this, for first 8 bits information, you kindly again check the LRC in your notebook and let me know if your LRC is matching with this or not. You all have understood how to calculate the LRC, right? Based on this data. Now during the transmission, some bits got corrupted here. LRC will remain as it is as the previous thing. But since data stream have got corrupted, so definitely there will be some mismatch between the parity bit of the parity bits of the bits in the data. with the LRC, because LRC has not changed while transmission. So there will be the mismatch, and since there is a mismatch, the receiver circuit will understand. The receiver circuit will understand that the data bit have got corrupted somewhere during the transmission, and therefore the whole data, expanded data, will be discarded, giving back acknowledgement message that kindly resend the data again. They will tell the transmitter, the receiver will tell the transmitter to kindly resend the data, because whatever data you transmitted, you sent, it got corrupted during the transmission. All have understood that if error occurs, then there is a mechanism in the system which will take care of if there is a mismatch between the data unit and the LRC bit, right? And with this mismatch, the receiver will understand that if error has occurred or not. If you look at the limitation of this, there are limitations of this as well. Now, you all have understood how I have calculated this LRC. See the right extreme column, where there are four number of ones. Four number of ones are there, which is even number of one. And since even number of ones are there, I am writing a zero here. Why zero? Because there are already even number of one present in this column, right?
Yes, sir.
If during the transmission, if during the transmission, if this one becomes zero and this one also becomes zero, this in row one, this first data stream, the last bit suppose becomes zero here, and here also last bit becomes zero, then how many ones will be there here?
Sir, could you repeat the question?
I am asking, if during the transmission, can you see the mouse pointer which I am moving around here?
Yes, sir.
Okay, if during the transmission, if this one becomes zero and this one also becomes zero, if this one becomes zero and this one also becomes zero, there will be two one only, and LRC will remain the same. So is it possible for the receiver checker to uh, uh, come to this conclusion that error has not occurred or error has occurred?
No, sir, we can't say definitely.
Because our algorithm is simply based on to count the number of one. So if number of ones are even and if LRC is showing zero, then there is no way that the receiver will understand if error has occurred or not. Whereas, but error has occurred already in the data, right? Right.
Yes, sir.
Okay. So this method again will fail in that case. Understood the limitation of this method?
Yes, sir.
Hmm? Okay. So with this method, if this one becomes zero, this one also becomes zero. There will no mismatch, and the method will be not able to detect the error. Okay. So till now, whatever methods we have seen, those methods were just based on to detect the error, if any, that might have occurred in the data unit while transmitting through the channel. But none of them were able to tell the receiver. Suppose if the error has occurred somewhere, but none of the method were able to tell the receiver at which bit point, at which bit location the error has occurred. You take the simple parity bit method, what we have seen, first method, this one, the vertical redundancy check method. So this was a 8-bit data. Suppose if you take and you append one more bit towards the right end, okay. If it is zero, no error. If it is one, error has occurred. Right? Understood? Right? No. This was
Yes,
like
sir.
this. No. See, this was like this. So this is 3, 4, 5, 6, 7 bit of information. If there are total number of ones are odd, then you append one more one. Okay. So this method and the next method also, the longitudinal redundancy check method. So these methods are able to tell the receiver that error has occurred if there is a mismatch between the parity count, parity bit, and this total number of one. Then then a receiver will understand. Okay, but none of these two methods they have the provision of telling the receiver that the bit at this particular bit position got corrupted. Am I right? If fourth bit got corrupted or fifth bit got corrupted or seventh bit got corrupted, there was no provision in these two methods. Am I right?
Yes, sir.
Okay, so since there was no provision of identifying the error bit position where the bit got corrupted, the bit position. Okay, so there is no mechanism, there was no mechanism to correct those error bits since the algorithm was incomplete in that sense. Algorithm was completely dependent on to just see if the total number of ones are odd or even. Okay, if the total number of ones are even, then you put zero, you append zero. If the total number of ones are odd, then you append one. Okay, so just algorithm was completely based on if error has occurred or not, right? If zero is appended, then no the total number of ones are even. If one is there, then total number of ones are odd. So these two methods were just to inform the receiver that if error has occurred or not. Okay, and then kindly resend the message to the transmitter to kindly resend the whole data unit again. So none of these two methods were able to detect the bit position where the data got corrupted. Understood? Yes? Hello?
Yes, sir.
Okay. So another method was developed to do two tasks. One is to identify the error, if any, and also to tell the receiver that at which bit position the data got corrupted. So these two tasks were then incorporated in another method, and which is a very good method, which is a very good method, efficient method, which is still utilized in small bit thing. Okay, not 1 gigabyte, not a large bit of information, but that method is still utilized where you have small bits of data communication happening. So that method we will discuss in the next class.